Hi, this is Raj, and with my team members, Swati Purushottam, we'll be presenting our project Mortality Prediction in the ICU utilizing topic models and burstiness. The objective of our project was to build a machine learning model that is used to predict the mortality of ICU patients based on clinical data from the MIMIC3 database. Our model specifically utilized free text clinical notes, which is really highly underutilized within the field. In addition, we utilized vital signs data and lab events to predict mortality. We also explored the use of burstiness parameter to really factor in the temporal nature of clinical events. There's a huge clinical need for our project for many factors. One being ICU patients cost a substantial amount of money to take care of and are a burden to our healthcare system. Additionally, clinicians always want the most up-to-date information, and understanding a patient's morbidity at the right time and at the right place can help better treat patients and allocate resources better within the healthcare system. So by analyzing patients' vital signs data and clinical notes, we aim to provide an accurate prediction on the morbidity of the patient. Our work is largely based off of Gissemi, who used LDA on clinical notes to predict mortality. Additionally, Bonamy, who utilized burstiness to predict length of stay in ICU patients, was also utilized. We aim to combine these two approaches to use burstiness and LDA to improve our prediction model. For our experimental setup, we utilized Apache Spark and Scala. Specifically, we utilized the MLlib package for SVM and LDA. For our dataset, we utilized the MIMIC3 database, and this was locally installed using Postgres. For pre-processing, we used Python and scikit-learn libraries. We used a MacBook Air laptop with 16 gigs of RAM to do our data analysis.
Hi TA, this is Swati and I'm going to explain you the system architecture and data processing used in our project. System architecture, we have used Mimic 3DB to extract structured and unstructured feature. We have added new concept burstiness in a structured feature. We aggregated those features for each patient and ran through supervised algorithm SPM. On the right side, we have tried to explain data processing and corresponding software used, extracting and creating views using PostgreSQL and then cleanse the data using Python script. We used Spark Scala to create and process the aggregated features, and then used Python MLlib to draw the chart of ROC scores. In this slide, we try to explain the motivation behind selecting those structured features. Example, we see clearly there is no dependency of age of newborn with mortality, so we have removed the age of newborn from age score, and we have only considered adult's age while creating views. Second example is of SAPS2 score. We see clearly SAPS2 score has dependency on mortality rate. On the right side, we have included the SAPS2 probability calculation formula used in our project. In this slide, we have tried to explain the variables and corresponding tables used to create each type of dataset. In this slide, we have tried to explain new feature burstiness and intuition behind selecting this feature. We have focused on temporal model, where temporal sequence is an ordered sequence of medical event. In this case, event is length of stay. Under this model, we aim to analyze the interval time sequence of ICU patient to study relation between mortality and length of stay. Example given, one patient that has regular visit and the other patient that presents subtle changes in frequency in visits. Irregularity in the second patient may reveal the presence of critical events in the medical condition of possible complication. We have tried to capture this using this chart. On the right side, we have given the formula for calculating the burstiness, and then we have included the Python script snippet to calculate this burstiness parameter. In this slide, we have included the code snippet for a structured feature.
LDA was used as an unsupervised generative process to create the top 50 topics for all clinical notes. Then a topic distribution was retrieved for each note as an added feature to be used in our prediction model. As you can see, in topic 1, the attributed features are heart, aortic, and cardiac, which represents heart failure. When using SVM, the best ROC value was 0.74 when using a combination of base features, burstiness, and topics from LDA. By adding burstiness parameter, it did improve our prediction by 0.03 as opposed to just using the base features. Our experimental results show that single layer ANN provides the best ROC curve with a value of 0.739, while the lowest being linear SVM. In conclusion, we were able to develop a mortality prediction model with the best ROC value of 0.74, which is close to published literature values. We introduced a new parameter, burstiness, to factor in the temporal nature of clinical events. Our future works include improving processing time using AWS and trying different supervised learning algorithms. Thank you, and below are our listed references.